Okay, so we're beginning with the business end now of this lecture. First of all, let me do the screen share. Here we go. All right, share. Okay, so when we what we've been looking at so far in the system, in testing in this course, we've been looking at the system under test itself, system under test, okay? And we're looking at the different structures that exist in it. Obviously, it started off with some source code, which we then turned into a control flow graph. And then we decided to analyze that control flow graph, maybe through a structural aspect, or we decided to look at the dynamic aspect, not the dynamic, I mean the data flow aspect of the internals of that software. Okay, but nonetheless, what we're doing is we're looking inside the source code, we're looking inside the system under test, SUT, a term that you're going to come across quite a bit if you get into the whole testing field. And what this chapter is actually saying, all right, so that sounds good, saying that, it's good to look at the software that you have, the internals of it, um, you know, sort of like white box testing, because we're looking at the structure of that graph and so on. But let's consider testing from a completely different perspective, all right? Ultimately, we we get some input, we have an input domain that is inserted into the system to get some sort of an output. Okay. Now, instead of looking at the system under test itself, its structure, and analyzing it in a systematic way, why don't we analyze the actual input domain? All right. That's the concept here of this chapter. This chapter is called input space partitioning. Now, I'm going to simplify the concept to the absolute nth degree. Okay. So here you are, you got the system under test. It's got 60 classes. All right. Hundreds of if else statements, loops, you know, data flow going all over the place. Okay. Just as a guess, how much time and effort do you think is going to take you to, do all this call sites and the integration testing and all that stuff to come up with test cases that satisfy test requirements that um, that are there for certain coverage criteria? You're probably thinking it's a lot of time, okay, a lot of effort, a lot of time, because first of all, it's a lot of test requirements and so on, and this is why we're going to need to have a lot of test cases. Okay, we're going to have a lot of test cases. Now, assuming the same software that we have, and with that very complicated structure, 80 classes, hundreds and hundreds of if-else statements and while loops and so on and so forth, and even the complication that comes with object orientation. Assume we have that system and all it has in its input space, it only takes one variable, x. And x could be either 1 or 2. This is only two values that it can exist. Well, instead of going through all this hassle of the graph coverage and data flow and the call sites and so on and so forth, coming up with test requirements for prime path coverage and edge pair coverage, one shortcut, I could say, is that we can just take the x as 1 and put it in the system, see if it works. We take the x as 2, put it in the system, see if it works. And if it works, I don't really have to worry about anything else in the system under test. Correct? Don't you think so, guys? I mean, that's an extreme scenario, but from a logical perspective, there could be some things in the system under test that actually doesn't work. But maybe X being one or two, we don't actually come and touch these areas, or if there's a fault that produces an error, that error never manifests itself into being a failure. So we don't really care. Okay, X can only be two values, one and two. Well, we tried it with one and it worked, and we tried it with two and it worked, so it works just fine. Right, guys? Okay. Now, because we're not in class, I'd rather that you actually type as much as you can so that I can actually see some engagement, because I'm just talking to a white screen here. So I would appreciate it if you guys can just give me a two-way communication feedback here. All right, so everybody following me on this? Okay, good, good. All right, so the the premise of this chapter is to analyze the input space, break it down. All right. Obviously, it's never going to be as simple as we have just the one variable, and that one variable can only take two values. Okay. But let's begin with some terminology here. So here we are, we got our input space. Okay, this is my input space. All right. So I'm going to decide that I'm going to break down the input space. Okay, I realize it. This is it. Okay, so this is called the domain. And really, the red border is the same as the blue border. Okay, it's just we've identified the finite set of input that we can possibly have. Okay, so this is what we call a domain. And then next up, we're going to start to break down the domain into blocks. Okay, here the word here, this is blocks. Okay, to break it down into blocks, we use something called a partition scheme. Okay, so a partition scheme could be, I'm going to decide to go this side. Okay, so this is block one, this is block two, this is block three. Okay, this is a partition scheme. Okay, I could have decided to break it down into something different. Okay, I could have decided to break it down into a different scheme. For example, such and such. Okay, B1, B2, B3, B4. All right. And there's a bit of a design aspect to this. How we go about breaking down the input space. All right. Which partition scheme should we choose? Which partition scheme should we choose, and so on. Now, the point here is why we need to be careful when we choose the partition schemes is that the partition scheme needs to be two things. First of all, it needs to be what we call pairwise disjoint. All right. And the other one, if I remember correctly, it's called complete, just to complete. Okay. Now, what this means is, assuming I have my domain as such, okay, I decided to come up with a partition scheme as follows. Okay, this is one area, this is another area. Okay, this is the third area. So first area is as such. Okay, second area is as such. Third area is as such, and so on. All right. Now, if you notice, I have this little glaring area over here that I haven't covered. Okay. So this partition scheme would be considered incomplete. So that doesn't work. The partition scheme has to be complete, okay? So for example, when we're looking at the grading scale here at El-Attar University, we have um, a number of blocks, okay? A minus, B plus, B minus, C plus, and so on, all the way until F, okay? Now imagine somebody created a partition scheme that accounts for everything from A to D, but it doesn't account for the F, okay? So that would be a partition scheme that will be incomplete. And why is that a problem? It is because when, if I happen to choose a value, like say 30%, which falls under the F category, I haven't actually tested it, okay? So I need to test a value from A minus, B plus, all the way to F. It's not enough to just have all the way down to D, because maybe, just maybe, the values that are in the F range are the ones that don't work, okay? So that's situation number one, okay? The other one we're gonna look at is, whoops, in the case that we have something that is pairwise not disjoint, okay? So assuming I have this partitions, okay? This is one partition, okay? This is another partition, okay, great. And then I probably should have done that, okay? Okay, this is another partition, okay? And finally, here's the blue. I got that third partition over there, okay? The issue that I see with this type of partition scheme is that there is this part over here that overlaps between the red and the yellow schemes. Sorry, the red and the yellow blocks. That means that had I chosen a value from here, then I don't really know, does this value belong to the yellow block or does it belong to the red block? Okay. Now, this is kind of important for me because when I do pick a value, I need to be able to know what does it represent, okay? And if I have an input space where the blocks overlap, that is an issue that I have. So, for example, assuming that the grading scheme that I have for this unit for the University of Al-Faisal, which is not the case, but assuming that this is the case, the A range go from 93 to 100. 93, not 95, 93% to 100. And assuming that the A minus goes from 90 to 95. Obviously, that means that the value is 93, 94, 95 is overlapping between A and A minus. So if I do pick as an input test, if I do pick the value 94, that means I'm not really actually sure, am I actually testing the A range or am I testing the A minus range, okay? I'm gonna assume one of them, maybe the A. So I test it and I say, oh, well, the A is working, but I haven't actually made sure that the A minus is working. And I may be even completely wrong that I was actually, in reality, with 94, I was actually testing the A minus range and I didn't test the A range at all. Okay, so everybody, can you see like the issue if I have a partition scheme that is not pairwise disjoint and is not complete? Okay, everybody follow me on this? I needed to write something. All right. Okay, good. So we're going back up over here. And like I said, I could have had multiple partition schemes. Doesn't matter which one I finally come across, I have to satisfy two criteria and two properties, that is being that they are pairwise disjoint and that they cover the entire domain. Now, focusing on the concept of a block. the the concept of a block here is that instead of considering every test value individually, we might realize that a range of values represent a certain block in my input domain. Going back again to the grade scale, 95, 96, 97, 98, and 100%, all of them represent the A block. So in theory, had I chose 96 as a test, that satisfies the A block. In other words, I had tried out my software to see if it's going to award the letter grade A had I given a value of 96. Now, 96 from a theoretical point of view is just as equal and is just as useful had I chosen 97, 98, or 99. Okay. But bottom line is, had I chose one value, that should be enough. I don't really need to go 95, 96, 97, 98, 99. Okay. Obviously, the more the merrier, but it always comes down to having a finite amount of effort that you're going to spend in doing testing. Okay. So you want to consider the block as all the values inside of them are equal. Okay. So this was the A block. Okay. Oops. Then 95 really is the same as 96, 97, 98, 99, and 100. Now, having said so, one thing we want to do is, as a good practice, we're trying to choose what we call the boundary values. This is where the problems tend to occur, okay? 95 is where, I'm in that dangerous zone where maybe the array that I'm doing is, is we're reaching the boundary of that array, and it's conflicting and overlapping with the A minus range because somebody has set the A minus range incorrectly. Okay, that maybe they put the A minus range to be 90 to 95. So when I put the input as 95, suddenly I get an A minus instead of an A. This is what I'm trying to say is choosing the boundary values tend to be the ones that expose, you're pushing them to the limit. You tend to expose the failures and the faults. The ones that in the middle, what we call the comfort zone. Okay, it's okay to start off with the comfort zone. Okay, but if you're going to be doing more tests, or if you're going to have fewer tests to do, you might want to begin with the boundary values. Okay, the boundary values are the ones that tend to expose the issues that we have. All right. So this is the property, this is the aspect of blocks, that every value inside of them is equal. Now, input space partitioning, the partitioning, like I said a moment ago, is a design aspect. Okay. And you think it's easy that I just create a partition and that everything is going to be pairwise disjoint and it's going to be complete. Okay. It's not really as easy as we think. Okay. So if I go here to the side, let's just say I have this situation. I have a situation where I'm trying to test something that is dependent on the order of files that I have. Okay. You know how you open your file explorer, whether you're using a Mac machine or a Windows machine, and then you see the files are listed as such, right? And then you can click, say on the name at the top, it can be ascending, okay? Click on it again, it'll be descending, okay? Or it could be some sort of a third aspect, maybe an arbitrary order. I mean, no order in per se, right? So when we look at this, we think I'm going to create a partition scheme that is split into three. You got arbitrary, ascending, and descending. Sounds good, right? Does that partition scheme work? Is it pairwise disjoint and complete as well? I'm looking for an answer. What do you think? All right.
It could be complete, but I don't think it's disjoint
Okay, why?
because ascending and descending contain the same files as arbitrary.
Ascending is the same as arbitrary? No, no.
Contains the same files.
What? Can you-
Contains the same files as arbitrary.
Ascending is the same as arbitrary? Is that what you're saying? I'm
Con-
not sure I can hear you well. Contains the same. Yeah, I know. They contain the same file, but I could have something that goes like this. This is A, C, B. That's arbitrary. Then A, B, C ascending. Then C, B, A. That's descending. Okay, so three different orders that I'm checking. So even if they contain the same files, I can still have the same those three different orders. So I decided to have this as arbitrary, this as ascending, and this as descending. All right. And it looks at a first glance, ostensibly, that this satisfies the two criteria of being pairwise, disjoint, and complete. But what if I have a scenario where the file folder that I'm dealing with just has one file in it? Okay. This is a situation that I'm dealing with. So this actually satisfies being arbitrary. It also satisfies being ascending. It also satisfies being descending. Okay, this is exactly the same as when I was talking about the grading scale, when I have the A minus going from 90 to 95, and then the A going from 93 to 100. There's, it's not pairwise disjoint. Now, maybe this is what you were actually trying to say, Abdurrahman, and I just didn't understand you. All right. But like I was saying, at first glance, it looks like, yeah, sure, ascending, descending, and arbitrary, I probably cover it all. But this is not really necessarily the case. Okay. When consider the different scenarios that can exist, you can realize that the partitions that we have are not enough. Okay. That the partition scheme that we have are not enough. And that maybe I would have to decide on more partitions, okay, in order to make sure that they cover the two criteria of being complete and pairwise disjoint. All right. All right. So when we let me just go back again and let me just erase the canvas. Okay. So now what we gonna do now? Now that we understood the concept of the domain, we're gonna look at the partition and the blocks and the criteria. We're gonna get to the point of input space partitioning. In other words, I'm gonna be modeling the input space, okay? I need you to pay very, very, very close attention to this coming 5 minutes because this is where it really gets complicated, okay? Um, when I have my input space, all right, I realize I have certain variables, okay? A, B, C, this is my system. This is when I look at in my system and I say, well, I got A, I got B, C, D, and E, okay? And then A could be a certain range of values, B could be a certain range of values, C, D, and E, all right? And I wanna be able to put them into certain blocks, and those blocks will have the A, B, C, D, and D. Maybe just A, B, C. This one has maybe A, B, C. This one has just D and E. But anyways, together, they should cover the entire input space and that they're pairwise disjoint and also um, complete. Okay, so let me just delete this now. So going back again, this is my input space. All right, I'm gonna replace ABC with a football team. Okay, these are my players of my football team, and it's just a small football team. They're just 5 players. Okay, every player is a variable, like A, B, C, D, and E. Okay, now when I'm looking at the players, I figure that I've got something, an aspect called characteristics. Okay, صفة, characteristics. What would be, for example, those of you who like to play FIFA on PlayStation or whatever, what sort of a, or even just watch it on TV, what would be a characteristic, a general characteristic of a football team when they play
They have different roles.
as a football team in general, like as a whole team, looking at all 5 players at the same time? It's just a game of two halves. So it's not really that complicated. Guys, skill, all right? Skill is a characteristic, but let's simplify it even better. Let's just actually simplify formation. All right, well, uh, all right, well, that's also characteristic per se. But let's even simplify. Let me just cut to the chase here. I mean, let's just take even offense, or should I say attack. How good they are in attack. That's kind of like the most important aspect of a team. صح? That's horrible writing. Let me just write this again. Attack. Correct? And the other one that's opposite is defense. Okay. And they're using the same players. Okay. So I got player A, B, C, D, they're in the game. There's two parts of somebody's game. This is offensive game and there's defensive game. So some player could be really, really good at defense, but really, really bad at attack. And vice versa. Some maybe player that is good at both, and maybe there's a player that is bad at both. Okay. In order to realize how good the attack is, we're really using the inputs of these different players together. It computes some sort of an attack. So, assuming this is a really good team at attacking. So when I put in the inputs, I realize, I'm a certain level good at attacks. And I can decide this number, the 98%, based on different ranges. So once I get the numbers, maybe I can just look at things like skill, speed, dribbling, and so on. Together, a whole lot of formulations that I use to compute some sort of a number here at the end. Okay, that's really not our issues. Okay, kind of like the grading scale that we had at university. Certain numbers mean certain things and so on. And albeit the only difference between this and the grading scheme is that the grading scheme uses one value, whereas this is using multiple variables. But it's the same thing. At the end of the day, it's the same thing. It doesn't matter if it's the one variable or multiple variables. I'm computing an aspect. So a characteristic. So when we're looking at the grading scale example again, really the characteristic that I am judging of you as students is your academic performance. Okay. Does that define you as a person in total? No. Okay, there's different aspects about you. For example, your kindness, the charity work that you're doing. But the characteristic that I'm judging, okay, of you is just your academic performance, not the other characteristics. Anyway, and also to compute a number for defense, all right, I'm taking the same five values to compute. Maybe that's not a very good team in defense, so maybe it comes out to 70, and I'm going to compute the defensive capabilities of that. And obviously, this is team one. These are the numbers that come up with it. A different team could have had a different value, and a different team would have had a different value. And when you're playing PlayStation and you're flipping and you're scrolling through the different teams, you'll see those numbers, they change from one team to the next, to the next, to the next. All right. So this is the concept of a characteristic, okay? For each one of those characteristics, and defense, I'm going to be using the same partition scheme. Where is it? Let me just grab this. The same input space for both. Oh, did I just delete it? There we go. Copy. See, this is my input space. How do I do the paste? There we go. This is it. All right, and the same thing here. Okay. Sweetie, let me just move it up here a little bit. Why? Because it's the same 5 players. This is why I made a copy paste. It's the same 5 players. All right. In the attack, this is my input space. I'm going to decide on this partition. In the defense, I'm going to decide on that partition. All right. Now, there's a difference between this is a characteristic, and for every characteristic, given the same input space, I'm creating different partitions. Okay. So in attack, speed being equal to 100 puts me at, say, the best category. All right. Whereas maybe speed, hypothetically, being 100 puts me in the average category of defense. It's up to me to decide. It's up to me to decide. Okay. At the beginning of this lecture, I was saying something about creating different partition schemes. Okay. Now, a partition scheme means that for the attack, had I created a different partition scheme, I'm having the same input space and I'm deciding on a different partition. So I got blocks 1, block 2, block 3. This would be an alternative to that scheme. So this is scheme 1 for the attack. This is scheme 2 for the attack. And one of them can replace the other one. However, this one and that one, defense and attack, they're 2 different characteristics. They are 2 different characteristics. Everybody follow me on this? There's a difference between when I have a characteristic and I want to decide upon the different partition schemes, and I can, well, I want to choose I want to choose this one, or I want to choose this one, or I want to choose that one. That's fine. But obviously, when I have different characteristics, the different partition schemes are not alternative to each other. Each one of those characteristics has to have a partition scheme. Okay, it has to have a partition scheme. So I decided, well, this is the partition scheme that I have for defense. All right. So, so let me use some sort of a concrete value here again. Okay. Um, let's just say as a student, there's two aspects about you. Okay. There is your um, what's it called? Obviously, your academic performance, and if you, for example, your community service. Okay. So in the community services, things like, what sort of clubs that you're in, what sort of work that you do to serve your community, and so on as a student. And then obviously there's the academic performance, more conventional characteristic of a student. Are you doing good? Your GPA is 3.5 or above, or you're not doing so good, and so on and so forth. Okay. Now, academic performance, the way we have it at Al University, it was, A goes from 95 to 100. And if you think if this is my input space, so this is one block, second block would be my A minus, and so on. And then my A minus goes from 90 to 94. Okay, this is one partition scheme. Let's call it partition scheme number one. A different university, for the same characteristic, could have decided on a different partition scheme. For example, it would decide, wallahi, 90 to 100, that's A. And then 85 to 90, sorry, to 89, that's A minus. That's just a different partition scheme, but they are judging the same characteristic. That is your academic performance. All right. And the community service, no, we're talking about a completely different characteristic that has its own partition scheme, and it cannot be just replaced by the partition scheme that I had for academic performance, because they're talking about two different things. They're talking about two different things here, okay? So going back here up to this area. Now this is very, very important, guys, before I move on to what's gonna come up next. Does everybody understand what I just said? This is kind of like the most confusing part, the difference between different partition schemes and alternatives, and the fact that I have aspects, characteristics. Each one of them has to have its own partition scheme, and they cannot be alternatives to each other. Okay, every team has to have an attack characteristic and a defense characteristic, whether we like it or not, or whether they recognize it or not. And that the variables that are used to judge the defensive capabilities can actually sometimes be the same variables that I'm using to judge the attack characteristic. Okay, meaning that this is variable A, B, C, D, E, and it could have using the same ones with different ranges as A, B, C, D, and E. But looking at them saying, well, if A is 100, that for attack puts me in really good. Wallahi, 100 in defense puts me in the average category, despite it being the same value. Okay. Everybody, do you understand what I just talking about here? But because again, this is the most confusing part of the lecture. Okay, so I need to be sure that you do understand this before we move on. So thank you, Ibrahim. Who else? Everybody else understands? I need a yes from everybody before I move on. Because if you don't get this, everything else is gonna slip from this point on. Okay, just take a moment to write down yes, that you get it, or if you have a question. Okay, thank you, Fat Faye. Okay, good, 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 good. Okay, so that's good. If we could get another concrete example. Um, all right, what would be a good concrete example? What would be a good concrete example? Like Abdurrahman, let's just say you go to a restaurant, okay? It's different characteristics about the restaurant, okay? One of them, for example, could be service. Another one could be uh, the food quality, okay? And you can decide your own ranges for the food quality, creating alternatives for the character for the partition schemes, okay? What is it that you define as good, okay? One university decides that 90 is good enough for an A. Another university, like Al Faisal, decides that 95, no less, is what I would consider an A category. These are different partition schemes for the different universities, but it's for the same characteristic. Okay. Obviously, I wouldn't use the same numbers, okay, to judge hospitality as well as the food quality using the same using the same partition scheme. Okay, so maybe food quality or a variable of the food quality, for example, how hot the food was, or how presentable the food was, um, is an aspect or a variable that contributes quite heavily in say the service characteristic, but it doesn't really contribute as heavily in the food quality, because doesn't matter how you present the sandwich, it still stays the same. You get that point, Abdurrahman? Okay, so I have this variable about, say, how good the food looks. Okay, sure, I would consider that part of food quality, but I also consider part of but it scores a lot of points to me under the service category versus food quality, because in my point of view, doesn't matter how you shape the sandwich, it still stays exactly the same. Okay. Um, all right. So if this, if you if this is good, Abdurrahman, I'm not sure if I was able to make the point across. Um, okay, good, good. Right. Now we're coming to the business end of 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 that lecture, of that chapter. And basically, the business end says, طيب, you've identified two characteristics, attack and defense. All right. So you decided in attack, well, I'm going to have three levels. I'm going to have level A, B, C, and D. Okay. And in defense, you decided to have three levels. Okay. Um, Actually, let me instead call it something else. You got A1. So I don't confuse you. Got A1, A2, A3, A4. All right. And in defense, I have three levels: D1, the best, D2, followed by D3. Okay. So if this is the way I decided to partition my defense characteristic and the attack characteristic, my inputs would be, my tests would be to choose a team or have a team that's obviously is gonna score or be evaluated as one certain level of defense and one certain level of attack. So, for example, team one could be level A1 in attack and D3 in defense. Okay, team two could be level A2 in attack and D1 in defense. All right. What's for sure, what we cannot have for sure, is a team, all right, being A1 and A2. All right. Why? Because we made them pairwise disjoint. We made them pairwise disjoint. So I know for a fact I'm never going to have the situation because whatever values that I choose is never going to end up being in two categories at the same time. And this is what I was explaining at the beginning of the chapter. This is what I was explaining at the beginning of the chapter, is that why is it that we really, really care about having our partition scheme being pairwise disjoint, okay, and obviously complete as well, okay. So, all I decided, here's test one. Test one is team one. And I'm thinking, okay, test one, team one, okay, A1 with defense D1. So it's a very good team. And then test case two, test case one, test case two, be team two, attack A1, defense D2. Okay, and you can see where I'm going with this, صح? Okay, you can possibly see that I'm just running out those combinations. And each one of those, A1 and D1, A1 and D2, A1 and D3, each one of those is a test case on its own. Okay, and the test case is choosing a block, and combining it with a different block from a different characteristic and saying, well, this is your team. And we're using that team as an input to the system. And this is how it scores in those different categories. I'm going to put that as an input into the system. Let me see if the system works correctly and if it produces the right output. Okay. Does everybody follow me clearly on this? What happens if the partitions are continuous instead of discrete? You mean, well, yeah, I mean, we don't have that in software. Okay. Ultimately, we have to have discrete values. I'm not sure what you're saying, Abdurrahman. Yeah, we don't have that. Okay, the digital world, it enforces a discrete nature to our software. So we gotta have to have a discrete, not a continuous nature to our values and our inputs. Okay, everything that you're gonna create a variable for, that you're gonna numerize, you're gonna have to choose a value for it. You can't just say it's concrete, and everything that you can possibly think of, like say the different gray scales, okay, or even the different types of colors that exists. Every color has an RBG number. You know what an RBG number, right? Red, blue, and green. And it's basically the digital world trying to find a discrete equivalent to what human nature would rather otherwise consider as continuous. Okay, if you take something like sound, okay, in reality, it naturally is a continuous thing, but still, when it goes into a computer, it has to turn into digital, so it has to turn into discrete. Okay. All right. Is that clear, Abdurrahman? But what if we have A1? All right. Now, this is where we were going, okay? So remember, we had A1 in the grade scale. A1 to A100. I mean, it's a bit of a smaller example than the one that you're given, okay? What we decided, yeah, Abdurrahman, we're gonna separate this into blocks, okay? We're gonna separate it into blocks. We said this is the F range, D or D minus, then D and so on. So we kind of like break it down for ourselves. Obviously, okay, if I have 100,000 values, I'm not gonna create 100,000 blocks. That's not really practical. And normally it doesn't really make sense. Okay. I mean, again, back again to the grading example, really, 95 was equal to 96, was equal to 97, was equal to 98, 99, and 100, صح? So really, what's the point of making 95 a block, 96 a block, 97 a block, and so on? Might as well just put them all together in a block. If you have something from A1, if you have something from A1 to A 100,000, it's unnatural or it's unlikely that you're gonna actually need 100,000 blocks, Ya Abdurrahman. Okay, you should probably be able to look at your different data that you have and realize, no, I could have split down the 100,000 blocks into 100,000 values to maybe 10 blocks. Okay, exactly. Not redundant. It's not redundant partition. Okay. Now you're using the wrong words in Abdurrahman. Okay. So what we call equivalent, we group the equivalent values. We said 95 all the way to 100, and all the values in between are equivalent. So then I'm going to create a block A1. Okay. Your question is saying, what if I have A1 to A1? So you're basically telling me I already have 100,000 blocks. Okay. Now, what I'm telling you, you shouldn't actually be in a situation to even end up creating 100,000 blocks to begin with. Okay. Because if you look at the values at the bottom, I mean, it'll be just really poor design that you end up with 100,000 blocks. And you need to be able to look at them and realize, well, this number is equal to this number, this is equal to that number. So I'm going to group them into one block. Okay. All right. So had I come here to this grading scale and I just went 100 is a number, 95 is a number, 96 is a number, that's really just poor design. That's really just poor design. And honestly, it actually even violates the disjoint because 95 is A and 96 is still A. And so, I mean, well, no, actually, it doesn't violate the disjoint, but still, it's just poor design. And I'm putting a lot more effort than I really need to. Okay. And as we'll see in a moment, as we'll see in a moment, the when we create a partition scheme and when we start actually end up creating the test cases, uh, the more blocks we have and the more characteristics that we have, uh, we end up creating more test cases. So you want to be clever about this. You know, you don't want to spend forever doing your testing. Okay. Um, but also you don't want to compromise at the same. So basically, what I'm trying to say is, you know, you got to be clever about this, and basically, yeah, uh, uh, just create a partition scheme that groups the different values that you feel are equivalent, and you know, trying to reduce the number of characteristics and reduce the number of of um, of blocks in those characteristics. Okay, and we'll see that in a moment why. Okay, but again, going back again to here. Okay, you know, we said we have A1, we have category A2. Categories A1, A2, A3, A4 in attack. And in defense, we have D1, D2, and D3. Okay. Um, the actual test case, although we say A1 combined with D1, A1 is represented by a number of variables. Okay. D1 is also represented by a number of variables. Could have been the same variables because they're the same players, or it could have been different variables. It's fine. It's fine. Okay. But this is what it means to actually choose a block is you come here to A, you give that a value equals 1, this is equal to 3, this is equal to 15, E is equal to 10. Whoops, where did it go? E is equal to 10, and D is equal to a minus 4, for example. You're actually going to use concrete numbers at the end, okay? When I choose A is equal to 1, 3, and 15 for the C, this is representing, let me choose a nice color here. This is representing, let me be more clear. This is actually representing A1, okay? And those values for E and D are representing D1. All right. Is this clear for everyone so far? Okay. What it means to actually be choosing a block. Okay. So when you choose a block, you're not just choosing the block, you're seeing what variables are represented in that block. Okay. And what values that is considered acceptable in that block to represent that block. And then you're combining it with blocks from other characteristics. Okay, is this clear for everyone, guys? Just need to get a yes. Okay. Ibrahim, Banan, Faye, girls, Sadoun, Fad. Okay, so we're getting very close. So I'm really glad that you follow me so far. Let me actually erase this because I think it starts to slow down. There we go. Type. Here we are, we got characteristic 1, it's got A, B, C. These are the blocks. We got characteristic 2, and it's got 1, 2, 3. I just called it 1, 2, 3. Okay. So I decided, test case 1 is block 1 with block A with block 1. Test case 2, A with 2. All right. Test case 3 is A with 3. You see what I'm trying to do here, صح? Everybody follow me on this. Now, if you think about it, what is it that I'm trying to do here? What is it that I'm trying to testing every combination? Exactly. This is what I'm trying to do. I'm trying to test every single combination. Okay. And how many combinations, Ya Abdurrahman, am I gonna have? 12. How did you figure out that 12? Exactly. 3, which is this, multiplied by 4, which is coming from that gives me 12. All right. And with this, I haven't missed any combination. Okay. So I know very well that my testing is very sure. So basically, if this is attack and this was defense, then basically I have tested every possible team in existence that could have existed. Okay. Whether they're very good at attack, very bad at defense, very good at defense, very bad at attack, anything in the middle, I've tested all of them. Okay. Now the issue that I have here, Abdurrahman, what if I have, actually, I want somebody else to answer this question. What if I have a third characteristic? Okay. مثلا sportsmanship or skill مثلا. Okay. Entertainment. And it has 5 characteristics. So I got E, F, G, H, and I. Okay. I want one of the girls to answer this. How many different combinations am I going to actually have? Remember that test 1 in this case would be an A with the 1 with the E. Test 2 would be A with the 1 with the F. Okay. So girls, can you tell me how many possible combinations can I have? Faye, Banan, can you let me know what combinations you have? I can have. What did you actually say? Exactly. Okay, so it's 12 multiplied by 5, that's 60. Right? Let's just say I had another small category here, C4. You can see the number starting to get bigger, صح? Let's just say I have a very small category and it just goes like this, and this is 4 and 5. How many combinations that I have? I'm going to multiply this by 2. So suddenly, just by adding a new characteristic with just 2 partitions, that's the minimum, then I end up with 120 test cases. And you can see, oops, and you can see, come on, 120 test cases. And you can see how quickly this is blowing up, right? And you can see how quickly this is blowing up. But nonetheless, this is a very strong, and it's the strongest criteria. And this criteria, we call it the all combinations criteria. Okay. It's the strongest, but also most effort because it's equal, it has the most test cases. Okay. So maybe I'll decide I'll have something that is a little simpler. Type. Back when I had characteristic 1 and characteristic 2, I have A, B, C. Characteristic 2 was 1, 2, 3. Let's just say I'm going to create a different criteria, a little bit a simpler one. Okay. And I'm going to call this each choice. Each choice. Meaning that every block I wanted to show once in my test. So I create test case 1. I'm going to call that A with the 1. Okay, now I don't need to have A and 1 show up again because I already picked them once. Okay, how many test cases I'm gonna have? Can somebody be really quick on this? 3. Yes. Oops, last one. C3. Had I had the all combinations category, we know that the number of test cases, this is 3, would have been 9 tests, whereas here is just 3 tests. So you can see the difference. So now, ignore this. Let's just say I added a different category here. And we'll call this E, F, and G. How many test cases would I had with the each choice? Can somebody answer me? 3. Still 3. Okay, but with the all combinations, it would be 3 multiplied by 3 multiplied by 3, which is 27. Okay. Now, obviously, there's a big gap between 3 and 27. All right. And so we've established kind of like the weakest criteria. That's each choice. And we've established the strongest criteria, which is the all combinations. And in the middle, we're going to be picking a number of criteria so that we don't have to go either extreme. Okay, sure, we can use all combinations had we had the number of criteria small and the number of blocks in those criteria is small. Okay, but many times this is infeasible because maybe we have too many characteristics with too many blocks on those characteristics. But at the same time, maybe we don't have to compromise way too much to the point that we're choosing too few tests. Okay, too few tests. I mean, if we actually theoretically go C4, C5, C6, and each one of them has three characteristics, still I could have done the whole job. I could have satisfied the each choice coverage criteria by just the three tests. Whereas طبعا the all combinations is gonna blow up significantly. Be 27 multiplied by 27. I don't know how much that is. All right. One last thing before I let you go. Right. Had I had criterion one over here, this is A, B, C. So not criteria one, characteristic one. And this is called characteristic two. How many test cases do I need to have in order to satisfy each choice? Can somebody tell me? Three. Okay, that's correct. Okay. So basically, I'm gonna have test case one. All right, that's A and the one. So I combined those two. Next, I'm gonna combine those two. So test case two is the B and the two. And then I'm still missing C. So, and I've already picked up one and two. So I'm just gonna have to end up repeating one of them. Re-choosing, should I say, one of them. So I will say test case three is three and مثلا one again. And this is really how it goes. So if I had a third criterion, okay, and that third criterion had two more test cases, okay, I got E and F. How many test cases do I need to satisfy each choice coverage? Still three. Exactly, okay, because basically as I'm sinking down, I'll have to just delete this first. So C1 was it one, two, oh, it was ABC. As I'm sinking down, it's just freezing on me for a second. It's, frustrating. It's not as fluent as it was at the beginning. A, B, C, and this was, you said one and two. As we're syncing, guys, or selecting, we're saying we're going A like this, B one, two, and then we're back again to the same problem, which we're choosing, we have to choose something we've had before. Okay, طيب. Let's assume that last scenario before I let you go, I got a C4 and it has three categories, three blocks, 3, 4, 5, and 6. How many test cases do I need to have in order to satisfy each choice? Four. Okay, everybody else agrees on four? Okay, so the way you should be looking at it, and probably what Abdurrahman did and Banan did, is that you looked at the ones and you say, I'm picking the largest one, exactly the largest size. Okay, if I go from the bottom up over here, yeah, at some point I'm gonna repeat some of those. Okay, but at minimum, I'm gonna be doing the largest characteristics, not the largest criteria, Abdurrahman, it's the largest characteristic. I need to cover that. And with the smaller characteristics, I'm gonna end up reselecting some of the blocks that I've selected before. So the number of test cases when I have in each choice is equal to the largest characteristic, whereas with the all combinations, the number of test cases equals all characteristics multiplied by each other. All right. So I'm going to stop here today. And in the next lecture, we'll look at the different characteristics that can exist. And time permitting, we're going to be doing a whole bunch of exercises um, to get you to practice, 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 practice. Hopefully, by the time you're done with all this practicing, uh, you'll be really a master at this chapter. It's one of the more complicated chapters in software testing. So that's it for today, and I'll see you on Wednesday, inshallah. Make sure you attend on time, huh? Yalla, bye, guys.